Starting. Hello, everyone. Thanks for joining us for this week's Neo4j online meetup. We have something extra special today as Mark Needham, who is our regularly scheduled weekly host, is going to be presenting alongside Amy Hodler. Amy Hodler is the Graph Analytics and AI Program Manager for Neo4j. And you guys probably all know Mark Needham as Developer Relations Engineer for Neo4j and the infamous host of the Neo4j online meetup. And also, these two people, I may add, are authors of the soon-to-be-published O'Reilly Graph Algorithms book. So that's very exciting. I'm going to include a link in the chat window right now if you're interested in registering for your free copy for when the book does come out. You're welcome to do that. Also, we are going to have a data science online training that's going to be released soon. And if you're interested in registering for that, it's going to be sent out as an update in our regularly This Week in Neo4j emails that Mark sends out weekly. And if you are interested in signing up for This Week in Neo4j, if for whatever reason you don't get it, you can actually go into this link right here where it allows you to manage your subscription and just make sure you just sign up for specifically This Week in Neo4j. And we'll make sure to get that information to you when the data science online training becomes available. So just really quick, make sure you set your resolutions to 720 megapixel. You could do that on the right-hand side, bottom right-hand side of the screen. And also, if you have any questions while Amy and Mark are presenting live, you're welcome to ask them in the chat. If there is a space where I can ask them a question, I will happily ask them on your behalf. And if not, we can have some questions, Q&A at the end also. And if you have questions after the live stream and you are watching this not live, you can also actually ask them directly in the community site, and I will post a link to a thread where you'd be able to use to directly interact with Mark and Amy. So I'm going to hand it off to you guys. You guys can get started. Amy, hello.
Hello.
Welcome. Thank you.
Yeah, well, I don't think I've met many of you. I've been on just a couple meetups in the past, but work really closely with Mark and Karine. So I'm excited to talk a little more about the graph analytics and in particular, this time link prediction. So since most of you don't know me, I'm a program manager, which is a really ambiguous title, but basically my job is to help explain and evangelize what we're doing with graph analytics in general, and just more specifically help people kind of understand what's possible. So it's a really fun job, and I'm pretty excited to be here.
Yay!
Cool. Yeah, and then my name's Mark, like Karine introduced me earlier, and so what we want to do in this session is sort of Amy and I have, along with a few others, are trying to figure out what are like practical examples of what we can show you that you can do with graph-based machine learning. And so this session today is showing like a kind of an example end to end of the first one that we've started working on. And I guess the plan is that we will do more of these as we explore more what you can do with graphs and machine learning. So that's the plan. So I guess we could probably hand over to Amy now. So Amy's gonna start us off by sort of giving us an overview, sort of a lay of the land. Like what are we going to do in this session, and where does this fit in the sort of overall scheme of things in machine learning and applying graph analytics to that? Cool. So I guess we can give Amy control of the presenter rights.
Yes. So
great. Yep, can see everything.
Okay, awesome. Okay, so just a couple slides to kind of set the context for how does link prediction fit in with the larger context of what graphs can do with AI/machine learning. And there's 4 areas that we think graphs are going to really change what you can do with artificial intelligence solutions. One of them you're probably all familiar with, which is knowledge graphs, which help people build context for better decisions, through the connections. The other one on the lower left is graph accelerated machine learning. So are there ways that I can use the context around my data to sub-filter faster and feed information into my machine learning workflows a little quicker. So it's interesting that the two on the left here, knowledge graphs and just thinking about machine learning workflows, those are all those are both very operational. Like, how do I do what I'm doing today better? On the right side, we've got two, connected feature extraction, which we're going to talk more about today, and AI explainability. And connected feature extraction, you can think about it as just, features in general or connected features in general. How can I pull information out of my graph so that when I am making predictions, the accuracy is better, the precision, the recall is better, and just my general predictions will be better because I have more contextual information. And that is very much into the, future and model building and how do I do, how do I discover new things? Lower right-hand corner is AI explainability. And that's an area that is really just emerging. And you can think about that as how do I make sure that the decisions that are made through my machine learning models, my deep learning models, my AI solutions, how do I know that those are accurate? How do I understand and explain how those decisions were made? How do I follow that path? How do I know what data it was based on? How do I know the decisions are made? So those are kind of the four areas that we look at. Today, we're going to talk about connected features and adding that and adding more context to your machine learning so you can improve your predictions. And, if we think about, well, why would I want to do that? I think at a very base level, if we want to improve our predictions, we should be looking at relationships because they are usually the strongest predictors of behavior in general, whether we're talking about whether somebody's going to vote or not, whether somebody might be a smoker or not. That's more likely to be predicted by their friends than it is in their friend network than it is necessarily specific demographics. So this is a really good book. If you're interested in this topic, there's a lot of good research in this book called Connected by James Fowler. So if we're thinking about improving predictions in your machine learning, I thought I'd use an example just to kind of give you a feel, and we're going to use a financial crimes example and just the kind of things that it may help and some of the processes. And we can think about that as kind of any kind of financial crimes. We've got money laundering, claims fraud, transaction frauds, all different types. And a lot of times we're trying to use machine learning to really kind of discover and learn these common traits. There must be some things in common that are predictive. Unfortunately, a lot of the machine learning models right now and methods kind of rely on this flat data structures and tables. And so you lose a lot of this predictive information, which is often in the relationships themselves. So by using connected features, we can help kind of uncover those. And there's a couple different, probably like three main different ways you can do that. The first one is engineering features. And that's really looking at improving your machine learning by calculating metrics when you know already what's predictive. So for example, financial crimes, how many people in my network are fraudsters? That's probably not a bad predictor of whether the probability that I'm a fraudster, might be higher. And that's much easier to do, especially when you're going many hops out with a native format that already has the connections built in. So if we look at this little visualization, we have 3 account holders, and might there be some activity here or some from fraudulent behavior, and we can go a couple hops out and we start to see some unusual connections, and maybe 4 hops out here we can see 2 hops out we can see 4 potential fraudster in this account holders network. And then if we want to even go farther out, we can also see some additional fraudsters. And this is something that can be very difficult to do with kind of a table kind of structure, because you have to do multiple joins, and scaling that and going many hops out can be very difficult. So this is a simple way you could use graphs to just add some statistics, score the number of fraudulent people so many hops out, and then you can use that in your machine learning as a feature later on. Another way you can use, or I think there we go, next slide. I think I actually combined them on slide. So another couple ways you can do that is looking at extraction and selection of the features. So you can use graph algorithms to actually uncover more predictive elements than you would have normally just on its own. And this is really good when you might know the structure that you're looking for. Like I want, community number. I'm looking for a really tightly grouped community, or maybe I'm looking for somebody with a high centrality, but I don't know exactly what that element is. I just know what the structure is. You could find anomalies. I mentioned tight communities, maybe a really tight community with behaviors that might indicate money laundering would be an example. And in this situation, we can use, on the left, we have a community detection algorithm. We're identifying these tight communities that have a lot of interactions, and maybe we'll want to sub-filter on that or score on that and then use that for the features. On the right side actually is another way you can use graph algorithms. For example, I think my example here is actually using centrality. I think I use PageRank to calculate this. But you can look at, of the features that I've scored, maybe I have 6, 7, 10, 20 features that I've scored. Which ones have the most influence in my network or in my model? And in that case, I can basically remove and get rid of the noisy features that don't have as much predictive power and eliminate the potential to have an overly narrow, overly fitted model. So those are a couple ways we can use machine learning to help us be more predictive and use graphs to kind of add in the predictive power and the accuracy and the precision that we have in our workflow without changing our workflow. And that's another element, is we don't actually have to change out what we're doing. We're just adding in better features and more features to that. So we're going to dive into link prediction. And the one thing I want to say as I'm handing this over to Mark is that just keep in mind that predicting relationships doesn't always require that you use an algorithm that's called a link prediction algorithm. We're going to show you some of those, but Mark and I have played with some examples where, depending on your data, you might actually be using a community detection algorithm, maybe label propagation, maybe connected components to come up with a score to then predict something else, and that might actually happen to be a relationship. So there are many different ways to do link prediction, and then of course there's a whole category of algorithms that are actually intended for link prediction, but those aren't the only ones that you can use. So I'm going to stop sharing, Mark.
Cool. Yeah, let me share my screen instead then. Can you see?
Yep, we got it.
Great.
Yeah.
Okay, so the plan for this next section is we're just going to quickly walk through. Okay, what is this link prediction problem? What's the kind of prior art? Like what research has been done in this area? Because this is certainly not a problem that Neo4j is the first to attack. It's been looked at for a while. Then we're going to show, okay, what support do we have in the Neo4j library, and then we're going to finish kind of the latter half of the session looking at how would we put this together into the machine learning pipeline that Amy talked about on the previous slide. So what is on the screen right now is a blog post that I wrote with Amy and our colleague Michael Hunger. And so we'll just start at the top and we'll just sort of go through. So what exactly are we doing? And Kareen's going to share this this post as well. So maybe I'll just zoom it in a little bit. So I guess the first thing is, as I said, so this topic has been researched for a long time. The first paper we could find when we were having a look was from 2004. So this was a paper written by John Kleinberg and David Liben-Noble, and they were researching. And actually, you'll find that a lot of graph algorithms research is done in the domain of social networks, and so this one was no different. And so they defined a problem as of this quote that we've got on the screen here. So imagine we've got a social network or a social graph, and we want to try and predict what new interactions are likely to happen in the future. And so in this social network, you could imagine that we had a Facebook graph, and the Facebook graph has details of the friendships that exist in here. And maybe on that graph, what we're trying to predict is, well, which people are likely to become friends in future, so that we can make some suggestions. So on like the Facebook right-hand side, where they say, hey, here's some people that you might want to become friends with, the people that we're showing there are actually like valid suggestions rather than ones that the person isn't likely to click and go, yes, actually that is a person that I want to be friends with. And so they that was where they came at it. So that's the kind of high level thing they're trying to solve. And so they identified that there are lots of metrics that they could compute. And the goal here was, can we work out how close, like, so two nodes that don't currently have a link, how close are they to each other? Like, how likely are they to have a link between them in the future? More recently, our colleague Jim Weber has mentioned this topic, not calling it link prediction, but referring to building triangles and triadic closures. And so he has a talk from way back in Graph Connect San Francisco 2015, so I guess more than 3 years ago now. And he's looking at how you can predict how World War II developed just by looking at the triangles that exist in this graph. But it doesn't have to be world wars, it doesn't have to be social networks, it can be lots of different use cases. So maybe we're trying to predict.
Mark, question. Actually, somebody asked in the Paul Starrett asked if it can be used to help design decision trees or CNNs.
I don't think we haven't tried to do that yet. So far, we've just been looking at given a graph which has relationships between things. Can you predict future relationships that are going to occur in that graph? I guess maybe we can show you what we've done, and then maybe you can we can loop back and see whether or not that helps for that problem.
Sounds good. Thank you.
Okay, but so it could be, so maybe we're looking for associations between people in a terrorist network. Maybe we're looking for molecule interaction in a biology network. Maybe we're looking for interest in an artist or artwork. And the one that we're going to focus on today in our example is co-authorships in a citation network.
Yeah, and, I was just going to say, one of the things I like to think about when I think about link prediction is, links are relationships. We know that, but they represent behavior as well. So in a way, you're predicting behavior, future behavior, and thinking about that when you're looking at your algorithms or trying to design the decisions can be helpful.
Yeah. So across all of these, exactly, some sort of future behavior. So if we just move on to the next section. So in this paper, they come up with like 10 or 12 different metrics. So here's a few of them. Some of them maybe some of them are reasonably simple. A lot of them don't require like difficult computations. Some of them, I guess, a little bit more complicated. All of them are trying to work out like how close are these nodes to each other. And I guess the thing to keep in mind with each of these is that depending on your data set, a different one might end up, or different ones may end up being applicable. And again, each of these metrics is trying to work out a measure of proximity or similarity between the nodes, and it's purely based on graph topology. So it's not taking into account any properties that nodes have or anything of that sort. It's purely based on the structure around them.
Yeah. So Mark, if they were interested in comparing like similarity of preferences or some property, they'd be looking at one of the similarity metrics that are also in the algorithm. Yeah.
So you might want to use one of those, but it wouldn't be one of these algorithms that we've categorized as link prediction algorithms. So what I want to do now is just show you. Okay, so there are a bunch of different measures. We thought it would be interesting just to quickly go through a couple of them. And show you how you would do this in Neo4j. So I'm just going to quickly go over to my second tab. So on here, this is, in case you haven't used it before, this is the Neo4j, the user guide for the Neo4j Graph Algorithms library. And you can see we've got several different categories of algorithms. So we started off a couple of years ago with 3 types. So centrality, community detection, and pathfinding. And in the last 6 months, we've added in these 2 extra categories. And so the one we're interested in today is link prediction. And so far, we've implemented 6 different algorithms. And so now this next section, I'm gonna split my screen. So I'm gonna move this over here, and we've built a guide. So if you want to play along, this is the, I don't know if that's big enough, Karine. Is it big enough now? Hopefully. So if you want to play along with this little example, you can type :play data-sciences/01.html. And so this is actually part of our online training, but I thought let's have a look at it now. So the idea here is that we've got just a little friends graph. So we can create this little friends graph. Yeah, I've actually created it already. So let's have a look. So this is the graph we're working with. It's a small one, just so we can understand what's going on. The interesting thing to keep in mind with this graph is that it's an undirected graph. So we're assuming that although on this diagram, obviously the nodes, the relationships have a direction between them, actually in our domain, we're going to ignore this direction. So by default, the link prediction algorithms will look at relationships and ignore the direction. But this is the graph that we're working with. So you can see B is kind of sitting in the middle, E is sort of off to one side, and the other ones have varying degrees of connectedness. So if we just come back up here. So one of the simplest measures, so maybe I'll put it on this side as well, is the common neighbors measure. And it is pretty much exactly as you would think. So we're just trying to work out, like, where are the triangles that need closing. So if we had a graph of myself, Amy, and Karine, imagine that I'm friends with Amy and I'm friends with Karine. Closing the triangle would be, okay, now Amy is friends with Karine. So it's pretty much what happens in real life. If somebody is friends with two people, it's quite likely that they end up becoming friends with each other. And so this is the concept of the common neighbors measure. There's a really nice website. Hopefully I get this name right. Ahmad Sadre, I'm going to say. So I'll share that link with Karine in a minute, and we can post that in there. But it's also in the blog post, so you can also click to it from there. And so all of these are described with really nice diagrams on this website. So with the common neighbor ones, the common neighbors one, we're just saying how many common neighbors do we have?
I think it's a calculation of the number of potential triangles is, I think, the official. Yeah. And then you get a higher score, obviously, if you have more potential triangles in common.
Yeah. So if we do it for like nodes A and D, we can see they've got two. They've got two in common. So maybe we can just let's open it up again. So A and D, their common neighbors are C and B. So C and B are common neighbors, and there seems to be quite a friendship ring sort of going on here. So it wouldn't be unlikely that A and D become friends at some future point in this graph. We could do the same thing for some of the other nodes. So we could do it for A and E. And so if we do there, for A and E, there's only one. So you can see that that's not such a strong connection, I guess. There's only one. So B is the only one connecting them together. And obviously, this is a very simple graph. So if you were doing it on your own data, you'd get a bigger range of numbers than we are likely to get on here. So that's one of them. So that's called common neighbors, and it's obviously very simple. It's just literally how many chances do we have of closing the triangle, as Amy said. And so you can see here in the blog post, we identified that this measure is exactly what Jim talks about in his Graph Connect presentation. Let's do one more. So Adamic Adar is an interesting kind of, let's say, variant on that, but using the neighbors. So a lot of these measures are looking at the subgraph surrounding a pair of nodes and trying to compute some sort of value based on that subgraph. The Adamic Adar, and so what you'll find if you go and research this is that each link prediction research paper, the output of that paper tends to be, hey, here's an algorithm that does better than all the other ones on the particular data set that's being researched. So there are loads of them, and a lot of them are named after people. So if you look at like some of the research, you end up with ones, and they often just combine some people's names together. So I guess if we add those ones into the library, you're going to have quite a long name to type. So for Adamic Adar, what this one does is it kind of works off the idea that, so again, it's looking for people in a social network who are people who are likely to be introduced by a common friend, but it then looks at, well, actually, people who have fewer number of friends are more likely to you have a bigger chance if you're one of their friends of being introduced than if you're friends with like a real social butterfly who's friends with everybody. And why would it be you out of like the 200 friends they have that would be introduced?
So I kind of find this one fun because the idea that that if you're friends with somebody who's like super like you said, a social butterfly, like there's like almost like a dampening factor to your friendship.
Yeah. I guess you hopefully don't think about it like that in real life. But it's a pretty accurate way of looking at it. And I'm sure everybody has like an experience of people who are friends with everybody, and you can sometimes get onto their radar of interest, and then you've gone away for 3 months while they loop through, talk to all the other like friends they've got. Whereas other people who maybe have a smaller but maybe like closer set of friends, they're maybe to be talking to each other quite frequently, maybe every week rather than every few months.
I'm a social butterfly, and my friends have definitely seen that experience.
Yeah, Karine rarely talks to us. This was
It's the online meetups once a week where we gather together and talk.
That's the only way. That's the only way we can get to talk to Karine. But yeah, like I said, when Amy and I were researching this, we were quite amused to see the names weren't like describing like what they did. It was always like the names of the people who created it went straight into the algorithm. So let's just have a look at this one. So this time we're gonna run it for the whole graph. So I mean, it's a reasonably small graph. So what this query does, in case you've not done much Cypher before, so what we're doing is saying, basically get all the pairs, all the nodes, get all the pairs of nodes, filter it so that we don't have the same node on both sides, because that wouldn't be particularly interesting. And then all we're doing here is because we know this is a bidirectional graph or an undirected graph, we don't need to compare like every node with each other twice. So we just do this little comparison to get rid of one of them from each side. And then we also, these different libraries seem to have a different interpretation of what it means. Like if two nodes already have a link between each other, what should be the result of it? So we've gone with the option of we'll just compute the metric anyway. But some other libraries, sometimes like they're kind of a bit inconsistent. So other libraries go, well, if they're connected, I'm just going to say 0 because you'd never want to run it, which kind of makes sense as well. But it's not entirely obvious what the result should be if there's already a link, because what's the point of predicting a link if there already is one? But what we're doing here is we're filtering out people who are already friends with each other so that we only get scores for ones that don't have that link. And so in this case, it's suggesting that across all the pairs of people that don't have relationships, A to D is the most likely one to happen, which is kind of what we had determined before. And then it's saying A to E, basically everybody else to E is less likely. So you can see they're all kind of, and B is excluded because it already has a link. So each of these, they have basically one in common. It's B. I guess you'd get a more interesting result if we had a little bit of a more complex graph. But that's the idea. So with most of them, the higher the score, the idea is the more likely there is to become a future link between those things. Okay, so that's the end of this section. What we then want to do once you've done that, so I've got these scores, and there are 4 other ones as well. But what should we do with them? So there are kind of 2 approaches. By the way, in the blog post we go through each of them. So if you didn't follow that last bit and you want to get the code and play around with it yourself, you can follow it through there. But what we want to do next is figure out, okay, what are we going to do? And there are two approaches generally that we came across. So the first, hang on, let's see if I can get this header to go away. Maybe not. So the first one is, well, we can just use those scores directly. And this is like a lot of the early research is actually taking this approach. And what that means is we choose like a threshold value. So for example, let's say for the Adamic-Adar score, maybe we say, okay, we're going to do all those comparisons of potential future relationships in this graph, and we're going to make the prediction that anyone who has a score higher than 1, that's likely to become a link, and we're going to make use of that information in our application. So maybe we're going to, for those people who have potential friends with a score higher than 1, we're going to put that suggestion on our imaginary Facebook sidebar. So that's okay. We can do that. That's certainly an approach. But it does restrict us to only one measure. So we'd have to choose which one is it going to be. I suppose you could then start to build like a little program around it and say, hey, if Adamic-Adar is bigger than 1, or if common neighbors is bigger than 7, or if preferential attachment is bigger than 20. So you could build like a little kind of rules engine around this if you wanted to. But I think an easier way that kind of does that sort of for you is to feed these measures into a machine learning classifier. And so this is where the idea of link prediction overlaps with what Amy was describing with the feature extraction approach that we talked about in the slides at the beginning of the talk. And so in the example that we're going to look at, the only features that we use are graphy or graph algorithm based features. But if we were doing this on a more rich data set, maybe we would bring in some just property based features as well. So it wouldn't have to be all graph related. You have anything else to add to that bit, Amy?
I don't, do you want to talk about the classifier, like how you evaluate your classifier, or do we want to talk about splitting and testing data first?
Yeah, let's do that to begin with.
Okay.
So what you got to do now, so we're into machine learning land now, and so the way we've done this is, and we can share this as well, is we've got a Jupyter notebook that has a worked example for a citations data set. You can see it. Oops, sorry, I'm zooming the wrong side of my screen. So it's on my GitHub, so GitHub mneedham, and if you have a look under data science training, at the moment, this is, I forgot, Amy has a way of describing how I write material, and it's very much do this, do this, do this. There is at the moment not like supreme amounts of explanation between each section. But when this is, we're currently working on this as part of our online training, and so that in that version there will be a much more like explanatory version of this. The version there at the moment assumes that you're kind of working through it with me in the room, and I explain each step as we go. So let's just quickly, I'm just going to quickly zoom down a bit. So what we need to do is we need to choose a machine learning classifier. And so we'll just go to that bit. So generally, like the research in this area, it takes you typically to an ensemble method of some sorts. And so this basically often means we're basically building decision trees, some sort, and we're building lots of them. And this approach works really well when there's interaction between the variables that we're using. So what this means is that one feature might kind of compute another feature. So imagine if we made a model which has common neighbors, and it has Adamic-Adar, and it has preferential attachment. Each of those are topology-based features that use some information about the neighborhood. So there's likely some correlation between them. And there are some machine learning algorithms which make the assumption that each variable that you give them is kind of like uncorrelated with anything else. They sort of can stand in their own right. Whereas with a random forest approach, for example, even if there's some interaction between the features, so even if they're kind of correlated in some way, it doesn't matter so much. And so in the research, you sort of see people using gradient boost approaches or random forest. Those are pretty much the two that you see. But anything where either you handle the feature interaction yourself, or if you don't want to handle it, you need to pick one where it doesn't matter so much.
So Mark, do you find that the random forest classifier is just an easier way to get started if you're not sure what to do first?
Yeah, I mean, I'm not a data scientist, but from what I understand from reading stuff written by people who are much more skillful in this field, that's a pretty good place to start, and just to get a baseline of what you're able to achieve. And it's very, I mean, so we're using sciki-learn in this example. It's very easy to set it up and just put your data in and see, okay, what does it come up with? So yeah, that's
cool.
probably, I found that very easy place to start. So once we've decided that we're going to do that, as Amy, and so I've in the blog post, we've linked to like a bunch of research that other people have done as well. So we're kind of the curators of the research rather than the people coming up with the idea. We then need to figure out, okay, how are we going to train this model? So I'm just going to scroll a little bit up so we can see what the code looks like while we're doing it. Here we go. No, not here we go. Where do we go? Sort of around here. So with this and with graph-based, when we're sort of trying to predict stuff in a graph, it's very easy to mix up the training and the test sets. So at a high level, our goal is we want to predict like links between nodes. So in the example here, we're working on a citation graph. So it has authors, and authors have written papers, and those papers can cite each other, and the papers can be sort of hosted or published in a specific venue. And so what we're doing is we're creating a co-authors graph on top of that. So we're saying if two people worked on the same paper, we can consider them a co-author. So that's the graph that we're working with. And obviously people can co-author like multiple times. Like if they work together on two different articles or two different papers, that would mean we have potentially 2 different years in which they collaborated. And so what we've kind of simplified the problem a little bit here, and we say, well, we're just going to take into account the first collaboration. So the earliest collaboration is what we're interested in. And what we're trying to predict is when is the earliest collaboration, or actually just when is there going to be a collaboration between some people who haven't currently collaborated. Now, the first time we approached this problem, we thought, oh, well, we can just randomly pick out of the nodes where there's, or out of the authors who have worked together, we'll just randomly split that. We just used sciki-learn's split train test data function, and we're like, cool, all right, we can train this. And so we did it like that. We created some features, we trained a model. It was insanely accurate. And we're like, it seems like a bit too good to be true, and
we were cheating, yeah.
And we realised, with help from our colleague Andrew Jefferson, that we were actually cheating, because effectively we had allowed information from the test set to sneak into our training set, because we were training it on that data. Because in a graph, even if we'd completely split those pairs of nodes, there were still connections between either side, like of the data set. So we weren't really doing it properly.
Yeah, and I've heard that data leakage. This is actually a problem with very graphy data, because it is so connected. So you think you've split properly, but there's a connection, a backdoor, triple hop connection that you hadn't accounted for. And I think one of the ways is what Mark came up with, which is to look at time splits to help out with that.
Yeah. So I guess all the credit for coming up with the idea was again from reading the research of what other people had done. And so a very common approach is, if you've got a time dimension in your graph, as Amy says, a nice way to split it is to go, okay, well, we're going to pick a specific point in time, and we're going to almost split that into 2 subgraphs, one from before the state and one from after, and we're going to try and predict the after links. But we're going to train a classifier on the before links, and we're going to try and predict what happens in the after graph. So that's how we split the things that we're trying to the actual pairs of nodes that we're trying to predict. When we're running graph algorithms over it, when we're running it for the graph that we're training it on, we're not allowed to look at the links that are created on the other side of the time. So we can only look at links on our earlier time. But when we're running those same graph algorithms on the test set, we can take into account the whole graph. Like we wouldn't want to only take into account the later part of the graph, because we'll lose like a lot of the information. Like a lot of people have been working together for like a lot of the collaborations are sort of long running collaborations. They don't tend to be completely new, and so we want to be able to look when we're predicting the future graph. We want to be able to take into account the whole graph when we're computing our features. So that's part of the problem. So we spent a little bit of time figuring that out, and again, you need to come up with another approach that if the time isn't available for the data set. Once you've done that, so once you come up with that, that gives you the positive examples. So you're like, cool. So you've got, remember what we're predicting is two pairs of nodes, and what we want to say is, should they have a link between them? So we've got that. Now we need to come up with the negative examples that we're going to use. And again, we're going to come up with those negative examples again using the two graphs, the before and after. But as you can probably imagine, the number of relationships that exist in a graph is way less than the number of potential relationships. The number of potential relationships is the number of nodes squared minus whatever relationships exist, and then presuming you're not collaborating with yourself, minus the number of nodes. So it is massively bigger. So you have a really big class imbalance. Now we didn't make this error. I guess this was one of the few errors that we didn't make. But a potential error you can make here is to go, okay, cool. We'll use all those negative examples and our few positive examples, and what you'll get is a classifier that just says nobody has a link, and it will be really accurate because most of the time it's correct. They don't actually have a link. But it's not a particularly useful classifier, and we're actually more interested in predicting positive examples rather than just saying, hey, nobody's ever going to become friends. So we need to handle that problem. And there are kind of high level two approaches that we can take. We can either upsample the positive relationships so that we kind of reuse them up to the size of the number of negative examples, or an easier approach and that allows you to work with a bit less data is, we'll downsample those negative examples. So what it means is we want to have the same number of positive and negative examples so that a classifier can't just go, hey, everything is a link or everything is not a link. That will not be like an accurate classifier. And so you can see this on the left-hand side now, you can see the approach of how we've done it. So the bit that I've highlighted now is figuring out, okay, these are existing links on our early graph. And then to get the missing links, we're find the authors who have co-authored in this early side of the graph. And then when we were looking, we found like a variety of different approaches. It basically said the most interesting thing to do is find things that are in the neighborhood of a node, but obviously they can't be directly connected. So you want to look, and our first approach was we looked just 2 degrees out, but that ended up actually giving us a really overfitted model. So what we've tried instead is to do a mix of other authors who are between 2 and 3 degrees away from you. If I remember correctly, this gives you back 18 million pairs of authors, and there are only, how many was it? 80,000 pairs where they have collaborated. So we had to downsample this quite a lot. But we do this downsampling, and we do the same for our test set. So this time we're operating on the late graph rather than the early one. And then we can start to generate the graphy features. So I think I'm just gonna, so this is where the blog post ends, and we're gonna work on another one where we sort of go into a bit more detail. But if we just zoom in, you can see how you then apply those link prediction algorithms that we showed before. So what we're doing here, so we're saying I want to apply my graphy features. So this is just a function. We're giving it pairs of nodes or pairs of node IDs. And then we're kind of unwinding through those, so we're iterating through those pairs. We find the nodes that match them. And then we're computing common neighbors, preferential attachment, and total neighbors. And you can see here we're passing in the relationship type, which in this case is co-author early. When we're doing it for the test, it'll be just co-author. And what you end up with is a matrix that looks a bit like this. At a high level, what we're having to do is, because machine learning algorithms typically work with work with tabular data. So they work with matrices or tensors, you'll sometimes see it referred to. We need to put our data into a format that they can work with. And so what we've got here is on each row, we've got two nodes. We've got the label indicating 0 indicates there's no link between them. 1 indicates there is a link between them. CN is common neighbors. PA is preferential attachment. And TN is total neighbors. So that's another one that we didn't look at, but it's also in the Graph Algorithms library. We can do the same for our test set. So here's a sample of the test data frame. And then we're into running our model. And it's really simple. Like if you've used sciki-learn before, we're not doing anything super clever here. We're just calling the predict function. And in this case, we're just feeding in one of the features. We then compute the accuracy, precision, and recall, which actually now leads me to handing over to Amy for a little bit.
Yeah, great.
Mark, can you also post that GitHub link in the chat, please?
Yeah.
Oh, thank you.
Great. So once you start training your models and you start comparing how they've done. Oh, am I presenting?
I'm presenting.
You're presenting. Okay, good.
But I've got that slide on the screen.
Perfect. Okay. So these are just, I had to learn, what the nuances were different between these different types of measures. And it's kind of interesting. It really depends on your goal of what you're trying to get out of your model. So you'll want to tune, you can tune your models and then you can measure them, depending on what your goal is. So these are standard measures. You can, print this offline and, kind of refer to them later. Accuracy is kind of an interesting one. You'd assume, a high accuracy score and you'd be golden. But if you think about it, and my little description here is, if I have a model that predicts everything is a cat, and I happen to have 95 cats out of 100 in my data set, I'm 95% accurate, which sounds good, but actually maybe it could be, it's just everything's a cat. Doesn't matter what it is, it's a cat. So that's just kind of a one view into it. The precision and recall feel like the same thing. When you hear about them, positive identifications versus actual identifications. The way I keep this straight in my head is I actually think about, well, what happens if the score is low? So for precision, if the score is low, that means there are more false positives. So if I'm sensitive, or my boss is sensitive to false positives, I want to make sure that that number, the precision number actually stays pretty high. Recall, also called true positive rate, if that number is really low, if that score is low, what that means is I have false negatives. And so maybe I need to make sure that all the negative predictions are more accurate. Then I would want to make sure the recall was really high. It'd be great if everything was high, but if you need to tune for particular cases, you can do that. And then the false positive rate is the one that actually is the most intuitive. It does mean what it sounds like it means, and that's basically how many positive predictions am I getting that are incorrect, or what's the proportion of that. Mark, there's on the next slide, I just wanted to show people what some of the visualizations will look like. And you'll see this a lot in different research paper. They'll actually have these charts, and they'll talk about the ROC and the AUC. And ROC, or sometimes they can call it a ROC curve, but that's basically what a measure of the true positive rate and the false positive rate. And so you get these interesting kind of up and to the right curves. And you can imagine, let's say on this green line, so the line in the middle, what we would want to look at is, let's say I'm really sensitive to false positives, but I don't really care as much about the true positive rates. I'm feeling okay, about that, because I can get fairly high, in one direction, but maybe not the other. And that's kind of okay for me. The red line is actually better. So the more you kind of get to the left and to the top, the better your model is overall. And a lot of people will talk about the area under the curve. And that's kind of what we're looking for, accurate results overall. So what's the overall surface area for accurate results? So these things, you won't memorize them, but there's just things that you're going to see as you start to evaluate your models. Mark, is there anything else that you wanted to add there?
No, I guess the only thing is probably those first three measures are more useful if you're building a model to use in an application. But if you're trying to compare things against each other, you'll often find the way that people are proving that their model is better or their measure is better than someone else is via these ROC curves.
Yeah.
Cool. So just like to wrap up before we conclude, just want to show you. So we played around with doing common neighbors, then we bring a few of them together. So we try, okay, what happens if we do all three of these measures? Further down the guide, we do something that Amy described. So you can actually use community detection algorithms and have a look. Hey, do these two nodes come into the same partition? Or so you'll see, like, community detection algorithms refer to nodes having the same label or the same partition or the same set or the same community. And so we made a really simple. So this code here is just running the actual community detection algorithm. So in this case, we're running the Louvain and label propagation algorithms. And then we just made a simple function that called same community that just goes onto the nodes and checks if they have the same one. And I guess the other nice thing about the random forest is that we can get it to show us how important was each feature, like how much did it contribute to the model. And so it's interesting. So on this, the way to read this, so the common neighbors is still like having a really big impact despite being really simple. SL, I think, is same Louvain, and SP is same partition. So those are label propagation and Louvain. So those are having also quite a big impact. And you can see the triangles. So we computed triangles, and they weren't so helpful in this example. These are not the only ones we tried. We tried PageRank as well, but PageRank didn't really help in this one. But if you were trying to figure, if instead of computing co-authors, you were trying to predict potential citations of a paper, PageRank is really good because you tend to find that papers, like really old papers that are really well quoted, get quoted again. So like the seminal papers in a field tend to get re-quoted.
I was actually pretty surprised that PageRank didn't do well on this as a predictive, because when you do read some of the research and papers, there's a really good one on the spammer detection network as well that PageRank seems to do pretty well. So yeah, and that just kind of goes to show you just don't know until you kind of play with your own data.
Yeah. So Karine, I guess we can stop presenting, but we just wanted to just to summarize. So I guess the limit. So you hopefully you've seen that what we've done so far. It's quite easy to get started with, and it's reasonably easy to inject this into a machine learning classifier. The limitation of what we've done so far is this: what we've got in the library right now only works for what are called monopartite graphs. So i.e. the two nodes that you're working with have the same label. What that means in practice is that we're assuming that the topology between the two nodes is kind of similar. And so this would work for if I'm trying to predict a friendship graph, or if I'm trying to predict a citation graph, or if I'm trying to predict a co-authorship graph. It wouldn't work, and this is like an area of future research. If I'm trying to say on a Yelp business graph, I've got a user, I've got a business, there's reviews in the middle, and I want to know hey, which businesses is a user likely to review in the future? And the reason is because the topology around a business and then around a user is likely to be completely different. And so we need to, like, our next thing is to start to figure out, okay, how do we add to this library so that we can handle bipartite graphs, or kind of add a bit more flexibility around that. And so there are, if that's the problem that you have and you'd like to use Neo4j for it, let us know, like, what is missing, because we're still sort of researching around that area. And I guess to wrap up, I had we wanted to just to remind you of the links that Karine mentioned at the beginning. So the O'Reilly Graph Algorithms book has a chapter where we go through this this process. In that book, we're using Spark MLlib rather than sciki-learn. But we go through this and sort of explain the steps really, really closely. And this is in the last chapter of the book. Somebody mentioned on the chat that you can access this book on Safari. So if you have a O'Reilly Safari subscription, you can get an early access copy on there. If you don't, then make sure we'll have a free PDF version of this for you to get. And Karine's posted the link for that page at the top of the chat. And then we're also building this into an online training session as well, which we are still finishing off, but that should be hopefully finished in the next few weeks, and so you can try it out for yourself in a kind of guided exercise. I'm going to post the link to the GitHub chat that I promised I would do. But Karine, do we have any other?
I did ask if anybody had any final questions. And the only thing we got is Pascal asked if you guys are planning to expand the link prediction module to provide more tools or algorithms in academic papers.
Yeah, so we have. I mean, there are a bunch of ones that we haven't put in the library yet, and yeah, that's the plan. I guess.
Which ones do you want? That's the other thing. Yeah, there's so many. Which ones are most needed, I guess?
Yeah, if anybody's watching not live after the fact, please share on the community thread that I shared earlier in the chat window. I can repost all those links too.
Yeah. And Karine, I've posted on our Hangouts chat the link for the GitHub. You may need to post it.
I will post it. So this is. I'll post the link to the GitHub, and I will post the link to the community site where if you want to ask Mark and Amy more questions, you can do so there.
And one reminder for everybody, if you are going to be at the Spark and AI Summit in San Francisco, week of April something, third week of April, Mark and I will be there. We have a couple presentations, and then OzCon in Portland in July will also be there. So come see us.
Cool.
And like Pascal also said, oh, I'm sorry, go ahead, Mark, you talk and then I'll.
Shameless self-promotion. If you like the video, don't forget to like it so that other people will find it in the midst of multiple YouTube recommendations that they all get.
Yes, I definitely mentioned that in the chat window after the fact too, when we started. Let's see, so Pascal said popular ones, let's say path ranking algorithms. And it said it would be nice to have Neo4j for both data modeling and as a framework to implement some of the research papers for mining from Knowledge Graph. And then Joe Chisak said it would be cool in the future if Neo4j could receive an algo request, access how CPU intensive it is, and if it's too big, Neo4j could take control, send it out to Spark or Flink for processing. And
yeah, that might be a little bit beyond the remit of what Amy and I are doing in the graph algorithm space. But yeah, we can certainly figure out like how can we combine like Neo4j with other tools where it makes sense. And yeah, Pascal, if you maybe on the community site, we can talk a little bit more about which ones we should implement. Because there are loads of them. There are like 20 or 30 different ones that we could start with.
I'm going to post the link right now for the community site thread.
Cool.
So
otherwise, I guess we're kind of near it. We've already gone a little bit over the hour. Like immaculate timekeeping is not quite finished.
Pretty good. It's like 2 minutes over. Not so bad. Paul Starrett said, "Great job on the presentation." And David Vesey from Neo actually finished Amy's words. He said that the Spark AI Summit is going to be on April 24th and 25th. So.
Thank you.
Cool.
Thanks,
so we know when to go there then.
I'll be there too. I will.
Awesome.
Okay. So thank you guys so much for joining. And like I said, if you have questions, feel free to go to the community site. You can also subscribe to This Week in Neo4j if you want to hear from Mark every week. And then I'll get also all the cool updates on Neo4j stuff. Yeah, I think that's it.
Next week we're GraphQLing.
Next week we're GraphQLing. That is going to be really cool. You guys don't want to miss out on that. So the Neo4j online meetup, it's up there. I guess I can also post that one too. Although my assumption is that most people have that already.
Cool.
Great.
All right. Well, thank you for taking your time out of your day to come and watch. And yeah, if you have any questions if you watch this afterwards, or if anything didn't make sense, then feel free to ask us on the community site.
All right. Thank you guys so much.
Thank you. Bye.
Bye.